let us start today's session of synthesis of models and systems. And our focus today is going to be on probabilistic techniques, synthesis techniques. And we are going to have quite 4 distinguished speakers. And I would like to start first with Joost-Pieter Katoen, who is a full professor at RWTH Aachen University and the head of the software modeling and verifications, the MOVES group. He's also part-time associated with the formal methods and tools at the University of Twente and holds an honorary doctorate from Aalborg University. Joost-Pieter is since 2013 a distinguished professor at RWTH Aachen, and he's a member of the Academia Europaea. He's also a recipient of the ERC Advanced Grant. And the research of Joost-Pieter includes formal methods, model checking, software verification and synthesis, probabilistic programming, and concurrency theory. So there is much more that I could say about Joost-Pieter, but let me stay somewhat brief and give the floor to Joost-Pieter. So Joost-Pieter, the floor is yours.
Yeah, thanks a lot, Radu, for the introduction. I'd like to talk today about synthesizing probabilistic models and programs, and this is joint work with Milan Cieska, Roman Andrioshchenko, both from Brno University of Technology and from Sebastian Junges, who's nowadays at Berkeley. I'd like to start with an example, and that's about a randomized distributed algorithm, and the question is how to pick the optimal bias. So I want to look at what are so-called the self-stabilizing distributed algorithm. And just for your remembering, what is a self-stabilizing algorithm? It needs to be able to start from an arbitrary state, for instance, the initial state, and then convert to a so-called legitimate state. So in the token ring, a legitimate state is, for instance, a state with a single token. And then there is a closure property that says the system will stay in such a legitimate state in absence of any faults. And actually, this is a key concept in fault-tolerant distributed computing. There is even a conference that is completely devoted to self-stabilization. So there is this seminal paper by Dijkstra in the mid-80s who showed that self-stabilization in anonymous networks, networks where you cannot yet say use the identities of the nodes, is impossible. So this is an instance of such an impossibility result like Fisher, Lynch, and Patterson in distributed computing. And the solution by Ted Herman was, why don't we use randomization? So consider that we have a ring, and here is an example of such a ring, and read it in a clockwise manner. And we have an odd number of processes. Each process has a Boolean variable. And the only thing you know is your own variable, as well as the variable of your left neighbor, so anti-clockwise neighbor. And that's all you have. And then there are tokens, the black dots, which I'm explaining in a minute. So the algorithm is basically only 2 lines. So what does a process do? They all do the same. If your value is the same as that of your neighbor, then you flip a biased coin. If your value is different than from your neighbor, then you just copy the value of your neighbor. And that's it. And then a process is possessing a token if your value equals that of your left neighbor. And what are we interested in? We are interested in what is the expected number of steps until this algorithm is going to stabilize. Good. So here you see, just to see whether you understood the algorithm. Suppose we have the configuration over here. Then we first all the processes without a token. So those that differ from color. So for instance, this one has a different color than its neighbor because it's red, so it turns red. And the same, for instance, for this process, it has a different color than its neighbor, so it turns red. Now, all the processes that possess a token, they flip a coin. So we go in that direction. So this applies to the 2 green ones and the red ones. And for instance, this one apparently it still is green. That's the value of the local variable didn't change. But for this process, apparently, the coin flip said, I have to change my value because it turns from green to red. And now what we have to do is we have to basically assign the tokens. So that means that every process that has the same color as his neighbor now is going to get a token. So for instance, this process is red, its neighbor is red, so this process is going to have a token. Good. In this step, we didn't gain anything because we started with 3 tokens and we end up with a configuration of 3 tokens. But you can imagine that in another, let's say, possible outcomes of the coin flip, we indeed get from the situation where we have 3 tokens to a situation where there is a single token. Good. Now what you can do is, and this is what this table shows, you can automatically determine for which bias of the coin you minimize the expected number of steps to stabilize. And that's given over here. And here you see different ring sizes. And this is the size of the model. And what you actually have is here a kind of a Markov chain, but the probabilities are unknowns. They are variables. And those are the ones that you synthesize. And how to do that? We use abstraction refinement kind of techniques. I don't have time to go into details here. What is important that you see is that for certain ring sizes, you get basically 2 regions of parameters. So apparently there are 2 values for which you get a minimal expected convergence time. Actually, what we do, and here you see the curve, which is the blue curve. You basically try to abstract this. These are the yellow boxes. And then if they're not detailed enough, you try to refine those boxes, which is the picture on the right bottom, in which you refine the kind of regions in order to get more precision. That's intuitively what's going on. And you continue this until you're happy with, let's say, the amount of coverage of your algorithm concerning the parameters. So what you get is a picture like this. On the x-axis, you have the bias. On the y-axis, the expected recovery time or the convergence time. And what you see is that for small ring sizes, the one over here or the one over there, actually there is one minimum, namely a fair coin is optimal. But you see that for larger ring sizes, for instance, this one, I mean, 2 values are actually optimal, and there actually you have to use a bias to minimize the convergence time. Good. So you can automate this process and you can automatically synthesize the parameter values that minimize the expected convergence time in these algorithms. But probably we would like to do more. So the instance I just showed you is an instance of parameter synthesis where you have a probabilistic model like the Markov chain on the left. And in the Markov chain, you're typically interested in the probability to reach a certain target state, like for instance, this state. Or you're interested in what is the expected number of steps to end up in that target state. Instead, in the parametric setting, what we have are parameters. So here is the bias of the coin, x and 1 minus x. You're still interested in, for instance, reaching that state. But now we're interested for which values, so for which bias of the coin can we reach our target state with a certain probability. And let's say the probability lies among 1/6. And then what you can do, you can actually synthesize, and what you get is actually a rational function in the parameters, and you're going to check for which values of x is this the case. And what we get actually here is an uncountable set, because the variable x can have a real value, so we have uncountably many possibilities of finite Markov chains. The Markov chain itself is finite state. Instead, what we are currently also want to look at is actually what happens if I also allow topology changes. So typically, the cases where x equals 0 or x equals 1, that would mean that actually you would delete one of these edges over here, is typically excluded. So that means those parameter synthesis problems need to be topology preserving. So what if we also allow topology changes? Right? And that actually means we're not tweaking the parameters, but we're actually tweaking the control structure in terms of a program. So the idea is that, again, we have our Markov chains, but now it's possible to basically adjust certain parameters. So rather than having this backward edge to S2, it now goes back to the initial state. And of course, I could also define this going to this state rather than going to the initial state and so forth. So in fact, what we actually have is now a huge, but a finite set of finite Markov chains, in contrast to this uncountable set of finite Markov chains before in the parameter setting. Good. So what are we interested in? We are interested in, as input, having such a Markov chain family, this huge set of finite Markov chains, and a given property. The property could, for instance, be, we want to reach a specific good state with a particular high probability. And now we're interested in things like this. We want to find one Markov chain in the family, for instance, this one that satisfies our specification. Or we want to be interested in finding all realizations satisfying the specification. So in a sense, we want to partition our family into the good guys and the bad guys. And similarly, we want maybe to find the realization with the maximal probability to reach G. And that could, for instance, be this instance, yeah? Or something like this. And then you can imagine that, in fact, certain topology changes come with certain costs. And maybe we're interested in finding the cheapest one satisfying the specification, or the one that fits a certain budget that we define a priori. So these are the kind of things we are interested in. So the way to view this is that, for instance, if we have two parameters, one on the x-axis, the yellow one, and one on the y-axis, the red ones, and in this case, we have 18 different variants, then we are interested in finding, for instance, one of the members in the family satisfying the specification. So we're interested in, for instance, this is, for instance, one instance from the family. This could be, for instance, the topology on the right. This could be another instance of the family. That's the other topology, right? You see the difference in the red arrows. Or this could be yet another family. Good, I think this setting is clear. And now what we want to do is we want to partition the parameter space. So we want to determine which ones satisfy our specifications and which ones are going to reject or violate our specifications. Good, so the baseline is very simple, right? You fix the parameter, build the model, and you model check. So you just pick one instance. This could, for instance, be your instance. You discharge this to a model checker, and the model checker tells you, this model refutes the specification. Then you take the next one, and maybe that one satisfies the specification, and so forth. Now, this, of course, is a very simple strategy, but it's not using any of the structure from the family, and it's not going to scale. So another approach would be, well, you just take, for instance, those 4 family members and you're going to model them in one shot, which means basically that you're going to add one state here where you build a non-deterministic choice between the different family members. And that actually has proposed by people working on software product lines. This exploits some regularity, and you can use, for instance, symbolic methods for doing that, but it still, does not scale very well to large models. So we need to be a little bit more advanced to solve our thing. So the first idea is to use abstraction. So the idea is not to represent those 4 explicitly and then have one deterministic choice, but rather basically provide an abstraction where we forget the exact realization, the family member we are currently in. So we represent those 4 family members by a single model. This model is now a Markov decision process because it has a non-deterministic choice, because, for instance, here there is a non-deterministic choice between having those 2 arrows, for instance, in the model. So what we have is we have this non-determinism here. Now we have to be a bit careful, because if we resolve the non-determinism, of course, the resolution should be such that the resolved model indeed is a family member and not some model which is not in our family. But that's basically the key idea, the first idea, to use the kind of abstraction. Good, and this yields what we call a quotient Markov decision process. It's a quotient because of the whole basically family. So now what we can do using this quotient is applying a technique which is called abstraction refinement. Now, this has been developed already for probabilistic models earlier. So let's see what is special about what we are doing. So what we do is we take such a family and we model this by this abstraction as I just showed you. So we start with one abstraction. And here we have a queue of those abstractions, because what happens in our technique is that we're going to gradually, iteratively refine the quotient. So in the end, actually, we have a set of those quotients. Now we pick one element, we discharge this to a verifier. The verifier in green will check whether the model that we actually took is actually, which is an MDP, right? It's a Markov decision process, satisfies our specification or not. And if it indeed satisfies our specification, then we have found an instance satisfying our specification. If it's not the case, well, then we have to go back and select another quotient. And if the outcome is inconclusive, then the idea that we're going to refine the whole quotient family. And that means that we're going to split the family in several parts. If in the end we have checked all possible quotients and that quotient set is empty, then it turns out that our synthesis problem is not satisfiable. Good, I'm going to skip this picture. So what's the ID? Basically, this is the entire family. Suppose that this family contains these members. Some of the members refute the specification, some of the members satisfy the specification, and this was our threshold, for instance, larger than P. That is the situation, the individual situation. That's not the situation that we view, because the only thing that we have at our disposal is the whole family, actually the abstraction of the family. So the only thing we get by model checking is a minimum and a maximum. And from that, we can conclude basically nothing. So we get as a result inconclusive. So what are we going to do? We're going to refine the family into two parts. And for instance, we're going to look at these family members. Now, suppose that those family members are over here. That means in our abstraction, we get again a minimum and a maximum. The maximum is smaller than the threshold, which is over here, which means that all the family members over here refute the specification. So in one shot, we can decide that actually those are actually refuting the specification. And now the whole scheme is continued. Now you look at this blue part. Suppose that this is the situation. And here you see the result will again be inconclusive because we have both satisfying and refuting family members. So actually we need to refine. And we do this until at the end we get a subfamily like the two over here that, for instance, satisfy the specification. So in this way, we actually abstract. We start with an abstraction of the entire family and we gradually refine it so that we get subfamilies either satisfying or rejecting the specification. Another technique that we are considering actually is CGIS, where the idea is that we don't use this abstraction at all. We just take the family as it is. So that's my family of finite Markov chains or finite programs. And now what we do is we pick an instance. We use an oracle to pick a certain instance and we discharge this instance to a verifier. Now notice that in my case, this instance now is a Markov chain, right? We don't use abstraction here. It's just a Markov chain. We discharge this to a verifier. If the verifier says accept, then we have found a realization satisfying the specification. If the verifier rejects the specification, it also will give you a conflict, a kind of a counterexample. And actually, we are going to use that counterexample to not only rule out the candidate that we just have checked, but actually we want to rule out the whole, in this case, the sub-candidates or many of the candidates, and that's actually this blue area over here. Of course, if in the end no realization is left, it means again that my problem is not satisfiable. And that means that, we did not find any family members satisfying this specification. Good. A short word about counterexamples. What is a counterexample in the context of probabilistic models? Well, that's a little bit harder than for non-probabilistic models. So if we write, for instance, a program, and this is a probabilistic program, And then what is a counterexample of such a probabilistic program that refutes a certain specification? Well, that actually is a subprogram. And preferably, you would like to have this subprogram as small as possible. So we're interested in finding a minimal command set of this program. Notice that we do not determine the counterexamples at the Markov chain level. We determine the counterexamples at the program level. I think that's an important asset of this technique. So this is a hard problem. So there are several techniques. So for instance, you can use a max-sat problem, a max-sat approach, or you can use a kind of greedy approach to find these kind of examples, kind of counterexamples. So here is an example of a couple of numbers where you see 4 different models over here with different space sizes and different numbers of transitions. So here in the first red thing, you see the number of transitions. But what is most important is over here, where this entrance actually says that is the size, the number of edges of the size of the minimal command set, so to speak. And on the right, so the one in, let's say, yellow, is the one that you compute. So you're not always able to compute really the minimal one, but hopefully you get close to the minimal one. Why are we interested in those minimal ones? Well, because we basically exploit the following property. In terms of a Markov chain, remember, we don't determine counterexamples on the Markov chain level, but we do this at the program level. But in terms of a Markov chain, a counterexample is a kind of a sub-Markov chain. And the idea is basically all Markov chains that share this sub-Markov chain will refute the safety property. So the smaller those sub-Markov chains will be, the larger the possibility will be to rule out many family candidates in one shot if you do synthesis. Yeah, so that's the reason why we are interested in this minimal command set, and we're not just interested in arbitrary counterexamples. Okay, I hope that clarifies the setting. Actually, what we also recently did is we tried to combine the 2 approaches. We call this the best of both worlds, where we have a learner in yellow, and we basically have 2 oracles. The abstraction oracle, the oracle I showed you in the beginning that uses an abstraction of the family. And we have this counterexample oracle on the right in light blue that is able to do basically this CGIS-like approach. And now what this combination allows you to do is actually for a while to do CGIS. And if CGIS cannot, let's say, progress anymore or not fast enough, then we can use the abstraction oracle. And we can also use results from one oracle to speed up, to accelerate the synthesis by the other oracle. This looks like, conceptually quite simple. I mean, if you, let's say, the details, is actually quite laborious and quite intricate to find out and to make this work efficiently. This all has been implemented in Python using Z3 as a satisfiability checker and the probabilistic model checker Storm to do the model checking underneath. So we used this Storm model checker. Here is a plot from a recent tool competition or a comparison of model checkers, where on the x-axis you see the number of instances, and on the y-axis you see the amount of time needed to solve these kind of instances. And notice that the y-axis actually is log scale. So we use the one that corresponds to the red curve, which is the Storm model checker. So I would like to give you 3 short examples. First of all, here is a program which is about a dynamic dynamic power management. So actually we are interested in synthesizing this power manager. Here you see a model which it can be in 4 different power modes. There can be jobs. They will be entered in those queues. We have high priority and low priority queues. So we have low priority and high priority jobs. If the queue is full, you lose a job. So what are you interested in? You're interested in minimizing the probability that the queue will be full, because otherwise you lose a job. And you would like to be able to minimize the expected energy consumption. So in terms of the challenge is we are basically synthesizing guards and assignments in such a control program. and this specification, which is basically a control program with a number of holes. So it's a program sketch where you start from, and the specification is what I said just before, a conjunction of expected number of lost requests and the energy consumption. So just to give you some numbers, in total, this number, I mean, it's not 19, but I think it's 16 parameters, 43 million control programs. So the family consists of 43 million Markov chains, and each Markov chain of this average size. Now, if you would just do the naive approach by model checking every individual program, this will take you more than 1 month. And the approach, the combined approach that I presented you will solve this in 9 hours. The second example is a partially observable Markov decision process, where you basically, depending on the location in this maze where you are not able to distinguish one location from another location, so it's partially observable. This is very hard, so determining an optimal strategy, for instance, to reach the exit of such a maze is actually undecidable. So therefore, and this has to do to the fact that those strategies need infinite memory. So if you restrict the memory, for instance, you use only positional strategies, I mean, memory basically only the current state, then you can actually solve this as an optimal positional strategy, but this is hard. This is ETR complete, which is between ETR complexity class is between NP and P space. And this is, intuitively speaking, as hard as finding the real roots of a polynomial. So what we want to do is actually solving this hard problem. And in practice, what you're considering is actually you consider finite state controllers with a finite amount of memory, and these can also be randomized. So here is an example of such a maze. You see, for instance, that these positions, I mean, equally colored positions are basically the same. That means you cannot distinguish between being in position 5 and being in position 10. And you're interested in minimizing the expected number of steps to exit the maze. And in this example, we have 1 bit of memory. So what you see, for instance, here, it says, no matter what will be the memory, that says this X, don't care. Then we basically set the memory bit to 0 and we move from 11 to 8. And actually, this has a model with 22 parameters, 9.4 million possible strategies. The Markov chain itself is very small, but still the number of Markov chains to consider is of course large. The baseline takes about 2 days, and in our approach, you can compute the optimal one in 1 hour. And actually, the optimal one is indicated in the plot that I showed you on the left. To conclude, I'd like to come back to the Hermann's randomized self-stabilizing algorithm I showed you in the beginning. Notice that there we just had a bias coin, and the bias coin is just based on your variable value comparing with that of your left neighbor. Now, what happens if you are maybe having a more powerful strategy? Maybe if you have some memory and notice something about the past, can you then improve? Can you then basically get a smaller expected convergence time? And this turns out to be the case. So you can, for instance, consider a model with a single bit of memory, and to make the problem discrete, let's say that there are 25 different coin biases that you can pick from. And in our setting, this means we have 7 parameters, 3.1 million possible strategies, and each Markov chain having about 1,000 states. The baseline takes 1.5 days, and the technique that I just explained to you can solve this in 17 minutes. And actually what you get is a strategy which is not completely obvious. Namely, initially you use most fair coins and you have your memory bit set to 0. And later, which means if you're possessing the token, you try to maximize the probability to keep the token. And actually then you're going to use highly unfair coins with a memory bit of 1. So you can, let's say, automatically synthesize non-trivial strategies using this kind of technique. I'd like to wrap up. I hope to have shown you a couple of examples. I did not show you software product lines, I only mentioned it. Keep in mind that we use both Seeger and Seegis as well as their combination. Well, I'm the first to admit that this is definitely initial work in this direction. I think there are a lot of things that can be improved, refinement strategies, which I didn't explain in detail to you in this talk. We also want to look at other models, not only Markov chains and not only finite families, but also infinite families and so forth. Here are some pointers for further reference if you're interested. And there will be a tool soon in which this all is available to you. Thanks a lot.
Thank you very much, Joost-Pieter. Great talk. Have time for a short question. Does anyone to ask a question? Please raise your hand.
Hi, Joost-Pieter. Here is Russ. Thank you for the nice talk. Just a quick question. You sort of made a distinction between program and Markov chains. Is there a translation between them? Can you tell us maybe quickly a bit more how you get from one to the other?
Yeah, there is depending on what kind of programming construct you allow, there is a translation from, for instance, Prism programs, but also other kind of programs into Markov chains. The only point is that they don't have to be finite. So here we restrict ourselves to finite state programs, right? If you allow non-determinism, then your program is no longer a Markov chain, but it becomes a Markov decision process.
Thank you.
All right, so I have a short question. So you were showing these families. So we listened to a talk that was using libraries, and the idea was to share as much as possible the code, So do you think that it would be possible in your case to have like a sharing of subprograms, such that you build incrementally, this way simplify the synthesis?
I think this would be possible, yeah. I don't see any
obvious
why it would not be possible, but yeah. So you mean you create family members by basically identifying which shared components, which shared pieces they have, so to speak, and then assemble other programs from it, right?
Yeah, it's like creating objects, with incrementally having methods such that you share as much as possible.
Yeah. Yeah.
Thank you very much again. Let's give it to Joost-Pieter, and let's introduce now our next speaker, who is Kim Lar.